In this video we are going to learn which is the polar form of a complex number, and we are going to see how to move from binomial to polar form and from polar to binomial form. So the first thing is that remember that we need to read these lines to make intro. If we want to use the complex plot and complex plot bin functions to plot easily complex numbers. So remember that we have to come here every time we open the file, we just press intro to these lines. So let's see what's the polar form of a complex number. Up to now we have represented complex numbers in binomial form, which is a plus bi, and we have also seen how to plot them in the complex plane. If we have a plot of a complex number in the complex plane, we can see that we have defined them using the x coordinate and its y coordinate, but also every point in the plane can be defined by its distance from the point to the origin and its angle, which is called argument, which is in the counterclockwise direction. So what we are going to see now is we are going to denote by modulus of a complex number its distance to the origin, and it's going to be denoted by r, and by argument its angle. So in order to properly pronounce these words, because these are two new words for us, so we can move here and select argument. Or also modulus. We can also see how to pronounce modulus, which is quite difficult word to pronounce. Modulus. So you can go anytime you need, you can go to the Merriam-Webster and press how to pronounce modulus or argument or radians if you need. So definition: the modulus of a complex number a plus bi is the distance of this point to the origin of coordinates, and it's denoted using straight bars and of z, and it's equal this distance using the Pythagorean theorem. We have that this distance is the square root of a squared plus b squared. The argument of a complex number is given by its angle with the OX axis in counterclockwise direction. It's denoted by arc of z, or also theta, which is an angle, and this angle is such that the real part is the modulus times the cosine of this angle, and b is equal, the imaginary part is equal to the modulus times the sine of this angle. The important thing is that the argument of a complex number is not unique, since we can add or subtract as many complete circle rotations, or in Catalan is set voltas, as we wish. So if we have an argument, an angle for a complex number, we can add 2 pi k, where k is an integer number, as many times as we want. So for instance, an angle of 45 is the same as 45 plus 2 pi plus 360 degrees. In order to have a unique argument, we define the principal argument. What is the principal argument of a complex number? The principal argument is the argument that belongs to the interval minus pi open, pi closed. That is, from all the possible angles, we select the one inside this angle. In Maple, we can compute the modulus and argument of a complex number using the ABS command and the argument command. So let's do this first exercise. We have the numbers 3, 2i, minus 4, and minus 4i, and we need to plot these numbers and compute its modulus and argument. So let's do this first using by hand. So we are going to plot the complex plane. Okay, so we are going to do this. Let's hope that everything can be plotted in this one. So we have the first number is 3, so it's 3, 0. This is z1, it's equal to 3. So if we look at the distance, z1, its modulus, it's 3, because the distance to the origin is 3, and its angle, or its argument, it's 0, because the angle is 0. The second number is 2i, so it's point z2 equal to 2i, which is equivalent to the point 0, 2. Now, if we take this number, the distance to the origin is 2, and the argument or the angle, as you can see, is 90 degrees, which is pi over 2. So this is the second number. The third number is minus 4, so now we move here and we do minus 4. So Z3 is going to be minus 4, so the distance is going to be 4, and the argument now it's pi. It's 180, which is pi. And finally, the last number, if 3, 4, 5, Z4 equal to minus 5i. So Z4, the distance is going to be 5, and the angle or the argument is going to be, we can put it in a principal argument, which is minus 90, which is minus pi over 2. So in this case, we have defined all the angles to be the principal arguments, but we can add as many circle rotations as we like. Let's check it out using Maple. So let's define Z1. Z1 is going to be 3. So its modulus is going to be 3, and its argument, it's going to be 0. Okay, so in this case, if we use the complex plot plane function, we have that this number is on the OX axis, so we have a 0 angle. So if we do the same with Z2, now let's do it again. Let's just do it in here. So let's just put Z so that we can change it for all of them. So now Z is going to be 2i, distance 2, modulus 2, argument pi over 2. If we plot it, we have an angle of 90 degrees. If we now put minus 4, what we get is 4 pi, and this is the plot. And if we do minus 5 times I, we got a distance 5 and an argument of minus pi over 2. Okay, so any point, any complex number can be defined using its modulus and its argument. So now you can move and do the exercise, these two exercises, one computing the arguments by hand and the other one using Maple. An important thing is that all the arguments we are going to use always radians and not degrees. You can use degrees just to take a little bit of intuition of what's going on, but you have to use radians. So what is the polar form of a complex number? The polar form or modulus argumental form is R subscript theta. So instead we are going to write the modulus and the subscript the angle. So for instance, in this case, Z1 would be 3, 0, Z2 would be 2 pi over 2, Z3 would be 4 pi, and Z4 would be 5 minus pi over 2. This is the polar form of a number. Okay? In Maple, in order to introduce the polar form of a number, we need to use a command which is called polar, and we just have to introduce two arguments, which is the first one is the modulus and the second one is the angle. So in our case, the first number would be, the 3 is going to be 3, 0. The second one, Z2, is going to be 2 pi over 2. The third one should be distance 4. Remember that the distance, the modulus, should always be positive, pi. And the last one would be distance 5, argument minus pi over 2. This would be the way how to define a number in polar form using Maple. Again, but let's say it again, the argument of a complex number is not unique, so the polar representation is not unique since the argument is not unique. So, for instance, this number here, Z, can have an angle of pi over 4 or pi over 4 plus 2 pi, or pi over 4 plus 2 circle rotations or plus 3 circle rotations, or we can also subtract minus 2 pi, minus 4 pi, minus 6 pi. However, if we use the principal argument, so of all the possible arguments, of all the possible angles, we are going to use the one which is in this interval. In this case, every complex number has only one polar form. So now that we know which is the polar form of a complex number, let's see how to convert a number given in binomial form to polar and the opposite way around. So, given a complex number in binomial form, we need to compute its modulus, so its distance and its argument. So, let's move a little bit here. So if I have a number now, which is of the form a, b, okay, so we have this complex number a plus bi, which is equivalent to point a, b. We need to compute this distance, which is going to be r. R is going to be the modulus of z, and by the Pythagorean theorem, if this is a and this is b, we know that r is the square root of a squared plus b squared. Okay, so the modulus is computed by just using this formula. And what about the argument? So now let's see what about theta. So we have that the cosinus of theta is going to be a over r. So we have that r cosine of theta is going to be a, and also the sign of the arguments is going to be b divided by r, so r sine of theta is going to be b. So the angle or the argument we're searching is the one that verifies these two conditions. In Maple, we can convert a number from binomial to polar by just using the convert command. So here we define a number 1 plus I. Okay, again you can come here, 1 plus I, you can do this. 1 plus I is going to be 1, 1. This is going to be the number. Of course, we know that this distance is going to be square root of 2, and that theta is going to be 45 degrees, so pi over 4. But let's see how we do it with Maple. So we use the ABS command to compute the modulus and the argument to compute the argument. Now we can convert them to polar by just putting modulus and argument. So this is how to convert from binomial to polar step by step, but we also have the convert to polar, which does it directly. So this is the modulus, this is the argument. And we can use the plot to see that indeed this is square root of 2 because this is 1 and 1 and this is 45 angles. Okay. So in practice, in order to compute the argument, we have two conditions. So instead of using these two conditions, what we do is we use the tangent. So the tangent of the argument is going to be b divided by a. So we can use the arctangent command to recover the argument. But there's only one thing that we have to take into account, is that the arctangent command always returns arguments which are between minus 90 degrees and 90 degrees. So we always have a number which is in the first and fourth quadrants. And if our number is on the second and third, we need to adjust the angle. Okay, so let's see how we do it. So here we have this plot. Okay, so we have a and b, and we compute the arctangent of b over a. Okay, so in this case, if a is equal to 0, so if we are like in here or in here, we have that if we are in this case, the argument is going to be 90 degrees. Okay, or if we are here, the argument is going to be minus 90 degrees, minus pi over 2 or pi over 2. Okay, so this is the first case. The second case is if we are on the first and fourth quadrant, so if a is positive, then if I'm here or here, the arctangent is going to work fine. So if I compute the arctangent, I'm going to have the number that I expect. Okay? But what about if I'm on the second quadrant? So if I'm on the second quadrant, so let's do it like in here. So imagine that I have a number here, and I want to compute the arctangent. I compute the arctangent of B over A. This arctangent is going to give me this argument, which is a different one. Okay, so how do I move from this argument to this one? I have to add pi. So in this case, my angle is going to be what the arctangent gives me plus pi. Okay, because the arctangent is going to give me a negative value here in the fourth quadrant, and then I add pi to move to the second quadrant. So from the fourth quadrant to the second quadrant. Okay, and a similar thing happens when I'm on the third quadrant. So when I have an angle here, okay, so this one here, what the arctangent is going to give me is going to give me this different angle. So theta is going to be the arctangent of B over A. So how do I move from theta tilde to theta? So what I have to do is, I can add pi, but if I add pi, I'm not going to have the principal argument. So what I'm going to do is subtract pi. So I'm going to subtract pi. So my theta is going to be the arctangent minus pi. Okay, this seems a little bit difficult, but it's not that difficult, because whenever you need, if you have a complex number, the first thing that you need to do is plot it. So you have something like this, and you plot it, A, B, and you have a plot. Once you know the quadrant, you know the argument, the range of angles that you can have. Okay, so then you move the arctangent back and forth. So this is in theory, but in the exam you're not going to have a calculator, so this is going to be a little bit more difficult. So let's see what happens if we don't have a calculator. So if we don't have a calculator, what we need to know is the values for the tangent in the first quadrant, and then know how to move from the first to the second, third, and fourth quadrants. Okay? So the first thing that we need to remember is this table here, where we have the angles that we need to remember, which is 0, 30 pi over 6, 45 pi over 4, 60 pi over 3, and 90 pi over 2. So let's see how to remember this table by heart, the memoria. Okay? So the first thing is that we have to put the angles theta 0, and then we put pi over 6, pi over 4, pi over 3, and pi over 2, which is 90, so 30, 45, 60, and 90. Okay, so you can put it like this. Remember that we are always going to work with radians, but you can use angles just to know how to do it. The only thing that you need to remember is the sign. So this is going to be square root of 0 divided by 2, square root of 1 divided by 2, square root of 2 divided by 2, square root of 3 divided by 2, square root of 4 divided by 2. Of course, now square root of 2 divided by 2 is going to be 0. Square root of 1 is 1. This stays the same, and the only thing that we need to change is the square root of 4, which is 2, and 2 divided by 2, which is 1. So once we know this, for the cosine function, we put it in reverse order. So we just copy the same line in reverse order. And for the tangent, remember that this is the sine dividing the cosine. So it's 0 over 1, 1 over 2 divided by square root of 3 over 2, square root of 2 divided by 2, square root of 2 divided by 2, square root of 3 halves, 1 half, and 1 over 0. So the first one is a 0. The second one is 1. We can subtract it. So is 1 divided by square root of 3. We have the same on top and bottom, so this is going to be a 1. And here we remove these 2's, so it's the square root of 3. So in the end we get the square root of 3. And of course this one is 1 over 0, which in this case is plus infinity. So this is how we remember this table. Okay, so 0, pi over 6, pi over 4, pi over 3, pi over 2, 0 and half, square root of 2, square root of 3, 1, 1, square root of 3 divided by 2, square root of 2, divided by 2, 1 half, 0, and the tangents. In this case, we only need the tangent value, so the ones in red, in order to move from binomial to polar. So we have these values here, which are very important. So these ones are the important ones. And we also need to know that if we get a minus on the value of the tangent, the angle is going to be minus the angle. Okay? So we also have these other properties. We can also check, for instance, if we take this value on the table, minus 1 over square root of 3, and we compute the arctangent, it's going to be minus pi. So if we have this value here for the arctangent, the argument is pi over 6. If we take this one here, square root of 3, we should obtain pi over 3. Okay, so let's do the first exercises that we have, always having in mind this table here. So the first number is z equal to 1 plus I. I'm going to use z1 and z2. Of course, you always should do a plot so that you have, so if I have a 1, 1, this is going to be z1, and the other one is 1 minus 1, so this is going to be z2, 1 minus I. In this case, since the exercise is easy, so we have to compute r1 and theta 1 and r2 theta 2. Okay, so by definition the first modulus is 1 square plus 1 square, square root of 2, and the first angle, of course, we know just by looking at the plot that it's going to be 45 degrees. Okay, but if we compute the arctangent of b over a, here a is 1 and b is 1, we get the arctangent of 1. Okay, so we look at 1 here in the table. 1 corresponds to pi over 4. Okay, r2 is going to be the same because it's going to be 1 square plus minus 1 square, which is going to be square root of 2. Here a is 1 and b is 1. So theta 2, we can also have a look at the plot, and of course it's minus 45 degrees, but if we do the formula, it's minus 1 over 1, arctangent of minus 1, and now if we look at minus 1 at the table, we have minus pi over 4. Remember that we can use the arctangent because we are on the first and fourth quadrant, so the formula is going to work. So let's do now the second exercise. So now we have two different numbers. z1 is going to be minus 3 plus 4i, z2 is going to be 3 minus 4i. So again, important to make a plot even though it's not quite nice, just to know where we are. So z1 is minus 3, 4. So this is our number. This is z1. z1 is minus 3 plus 4i, which is equivalent to the point minus 3, 0. So now we have that this is going to be r1, and this argument is going to be the argument of z1. So we are on the second quadrant. So let's use the formulas. r1, which is going to be the modulus of z1, is going to be the square root of minus 3 square plus 4 square. So it's going to be the square root of 9 plus 16, which is going to be the square root of 25, which is going to be 5. Now the argument, so it's going to be the arctangent of b over a. But we know that we are on the second quadrant, so what we are going to obtain is this other angle if we use the arctangent, so we have to add pi to move it from the fourth to the second quadrant. Okay? So what we do is we add pi, to this arctangent. Tangent of minus 4 divided by 3 plus pi. When we look at this, we don't have 4 minus 4 over 3 in the table, so this means that this angle that we are going to obtain, it's not one of the ones that we need to know. So in this case, we can just leave it like it is unless we have a calculator, which in this case, this value is going to be minus 0.92 radians plus pi. So if I add pi now, I get an argument of 221 radians. Okay, so whenever we don't have the value at the table, we need to do it using a calculator or just leaving like it is. And the second one is a minus 3. Minus 3 minus 4i, so this is going to be this angle here. This is Z2 equals to minus 3 minus 4i, which is equivalent to point minus 3 minus 4. We are on the third quadrant, so the distance is going to be the same because we have the same numbers. R2 is going to be the modulus, which is going to be again square root of minus 3 square plus minus 4 square. This is going to be 5. And the argument now, the arctangent of minus 4 divided by minus 3, this is going to give us a number, an argument, which is going to be in this. So instead of having Z2 or Z2, which is the same, okay, theta 2, we are going to obtain this other angle. So to move from this one to this one, we need to subtract pi. So minus pi. Again, the arctangent is not going to be, the arctangent, we cannot compute it using the table, so now we subtract pi and we get minus 221 radians. Of course, looking at the plot, if I remove a little bit of this, okay, you can see that the angle, this angle here, is the same as minus this angle here. Okay, so let's check the results with Maple. In this case, I'm going to define Z1 minus 3 plus 4i, and I'm going to directly convert this number to polar. Okay, so as you can see, we get the modulus. What the argument is not given as a standard angle because this is not going to be one of the angles that we know. So then we can do a valve so that we get this one. Of course, we can also compute it step by step using the abs command or the argument command. Okay, if we do the same in the previous exercise, 1 plus I, you can see that when I convert to polar, since if you remember these angles were easy, okay, when I do it, in this case I obtain the argument pi over 4. So now you can move to the test and try to do from binomial to polar form. Remember that you need to remember this table and then convert the numbers. So now let's do the reverse operation, converting from polar to binomial. So we are given a number z equal to r theta. So we know the modulus r, the distance, and we know the argument, the angle theta. And we want to compute A and B. So in this case, we use a trigonometric relations. We know that this is A and B. We know that the cosine of the angle is going to be, the cosine is going to be A divided by R. So A is going to be R cosine of theta. And we know that the sine of theta is going to be B divided by R. So that B is going to be R sine of theta. So if I have a number R theta, and I want to convert it to A plus BI, this is going to be R cosine theta plus R sine theta I, or what is the same, R cosine theta plus sine theta I. So this is the trigonometric form. a number z of which we know r and theta can be expressed as r cosine, this is the real part, r sine, the imaginary part, times r. Okay? So the difficult thing is that once we know r and theta, this is very easy. We have this formula, but we are not allowed to use calculators in the exam. So we need to know the cosine and the sine of the most important angles. So we know, we have seen this table before, we know that we have 0, pi over 6, which is 30, 45, 60, and 90, and we have the values of sine, of cosine, when the angle is in the first quadrant. So what we need to learn is, what about if the angle is in the second quadrant, third, fourth quadrant? So if we have an angle which is not of these, none of these ones, but it's in another quadrant, what do we do? So in this case, we are going to use the following properties. So imagine that we need to compute the sine of an angle which is in the second quadrant. So I don't have it in this table here. So what we do is, instead of looking at this angle, what I look at is at pi minus this angle, so this other angle. This other angle is associated to the first one, and the important thing is that here the cosine of both angles is the same and the sine change signs. So what we have is that if we have a theta which is between 90 and 180, what we do is we do pi minus this angle. The sine remains the same because this is the same height, and the cosine change signs. If we have on the other side an angle which is on the third quadrant and we want to move it on the first, what we do is we just add pi. So these two angles are the two that we are going to consider. In this case, the sine of both angles have different signum or sign, so we have a minus here, and also the cosine, this and this have different signum, so we have a minus. So if we have an angle between minus 90 and minus 45, we add pi. By adding pi, we move to this first quadrant, and then we just replace or put two minus in front of the sine and cosine. And finally, if I'm on the fourth quadrant here, I have my angle which is between 0 and minus 90, and I want to relate it to one angle on the first quadrant, so I just change the sign. In this case, the cosine is the same, so in this case this distance is the same in both cases, but the sinus here and here, it changed signs, so I have a minus in front. Okay, so we need to learn this table, and then we need to know that from the second quadrant we do pi minus the angle, the third quadrant we add pi, and the fourth quadrant we just change the signs. And this is again a representation of this. Okay, so if I'm given 120, I'm going to look at 60 degrees. The sine function is going to be the same, but the cosine is going to be minus the cosine. If I'm given 150, for instance, I'm going to add pi, I'm going to go to 30, and both sine and cosine are going to change this. So when I look at the sine and cosine of 30, I have to change its signs. And for instance, if I'm given minus 60, I'm going to go to 60. In this case, these two angles, they have the same cosine, but the sine change signs. So let's do this exercise. Consider these complex numbers and compute its binomial representation. So let's do this exercise. The first thing that we need to remember always when doing these exercises is that we need to remember this table. Always put this in an exam. So let's start. We have z1 equal to square root of 3 pi over 6. So from what we know here, the modulus is 3, the argument is pi over 6. So if we use the formula, we have r times cosinus of pi over 6 plus r times sinus of pi over 6. So since pi over 6 is in the first quadrant, we go to the table. Okay, pi over 6 is in the table. Its cosine is square root of 3 divided by 2 and its sine is 1/2. So I substitute square root of 3 divided by 2, 1/2. So I get 3 over 2 plus the square root of 3 over 2i. Let's do the second one. z2 square root of 3 minus pi over 6. So here r is square root of 3, theta is minus pi over 6. But now minus pi over 6, which is minus 30 degrees, it's in Q4, it's in the fourth quadrant. So now remember that when we are in the fourth quadrant, we need to change the sign. So what I'm going to do is first apply the formula. So I'm going to have square root of 3 cosine of minus pi over 6 plus the square root of 3 sine of minus pi over 6i. Now remember that I have this. I have my angle here, theta, and I will take minus theta. Okay? So now the sines change its sinum, but the cosine remains the same. So I can replace the cosine of pi over 6 minus pi over 6 by the cosine of pi over 6, but the sines, I need to put a minus in front. So if I take out this minus in here, I need to put it in front. So what I get is, now pi over 6 is in Q1, so I can go to the table, square root of 3, square root of 3 over 2, minus the square root of 3, 1/2 of I, which is 3 over 2 minus the square root of 3 divided by 2i. So now if I do it, I can do it using the polar. This is going to be a square root of 3 and pi over 6. And I can compute just by doing eval, its binomial form. This is what we got. And if I now change the sign of the argument, I get the same result that we got. Okay? As we have seen, we can convert any number using the eval command. This is what we have done. But here you have also a plot of the two numbers that we got. Okay? This distance is square root of 2. This is an angle of 30, minus 30, and then you have the A and the B. We have another exercise before finishing. Again, remember that whenever we want to do exercises, we want to have this table on front. So let's start. C1, 1, 0. Okay? Always remember that it's nice if we can make plots so that at least we know which quadrant we are in. So 1, distance 1, angle 0, this means that this is Z1. So in fact this is not going to be number 1. But if we want to use the formula, we can do 1 cosine of 0 plus 1 sine of 0i. We go to the table, cosine of 0 is 1, sine is 0, so we have 1 times 1, 1 times 0i, so this is 1. Okay? Second number, z2 is going to be 2 5 pi over 6. So we are going to use the formula 2 cosine of 5 pi over 6 plus 2 sine of 5 pi over 6i. Now 5 pi over 6, so this is 0, this is pi over 2, this is pi, minus pi over 2. 5 pi over 6, it's in the second quadrant, so 5 pi over 6 belongs to the second quadrant. So now I need to move to the first quadrant in order to be able to use the table. So remember that what we have to do is if I have 5 pi over 6 belonging to the second quadrant, I do pi minus the angle, which in this case is pi over 6, which is going to be in Q1. So I'm going to relate this angle, this number, to this other angle. And what I have is that in this case I have the same sign, but the cosine, this value and this value, they have a minus. So now what I have is 2, the cosine, so I want to relate this one with the cosine of pi over 6, and I need to put a minus in front because I have that these two values are negative, plus 2 sine of pi over 6. And in this case, since the sign is the same, this is correct. I don't need to introduce a minus. Sorry. So what I have is minus 2 cosine of pi over 6 plus 2 sine of pi over 6i. Now we move to the table. Cosine as a square is minus 2 square root of 3 divided by 2 plus the sine is 1/2. So this is minus square root of 3 plus I. Okay. Before continuing, what I can do is just check it. Okay. So what I'm going to do is define the polar 2, 5 pi over 6, and I'm going to evaluate. Remember that Control L introduces a label, so 4.6. Sorry, it's not a valve, it's a bulk. And I get minus square root of 3 plus I, as I need it. So let's move to the third one. So now I have Z3, which is going to be 3 minus 2 pi over 3. So again, and this is important, always make a plot. This is minus pi, this is minus pi over 2, and this is, here we have minus 2 pi over 3. So now we have an angle which belongs to the third quadrant. So what we have to do is, if minus pi belongs to the third quadrant, what I'm going to do, remember that when I'm here, I'm going to add pi. So I'm going to do minus 2 pi plus pi. It's going to be pi over 3, which belongs to Q1. So I'm going to go up in here. This is going to be pi over 3, and this is minus 2 pi over 3. So now I apply the formula 3 cosine of minus 2 pi over 3 plus 3 sine of minus 2 pi over 3i. And remember that now both sine and cosine, this is a negative number, this is negative, this is positive, this is positive. So what I'm going to get is that I need to change signs. So I need to change sine of pi over 3, sine of pi over 3i. And now we go, the cosine is 1/2, so minus 3 over 2, minus, this one is 3 square root of 3 over 2, so minus 3 square root of 3 over 2i. In the end, we can always check that if I have to have a number in the third quadrant, I have to have negative, real, and imaginary part. But we can also check it in here. So what I'm going to do is change 3, and now 2 pi over 3, and then I get the result that I expected. Okay. And one last example, Z4 equal to 1 minus pi over 3. So now, if I have a look at this, I have minus pi over 2 and 0. So here I have minus pi over 3, like an angle. So when I apply the formula, I would get cosinus of minus pi over 3 plus sine of minus pi over 3i. But minus pi over 3, it's not on the table because it's in the fourth quadrant. So remember that if we are on the fourth quadrant, we need to change the sign. So I'm going to consider the same angle but change by signs. So now you can see that the sine here is positive and here is negative, while the cosine is positive in both cases. So the cosine remains the same, but the sine, we have to change its sign. So now cosine of pi over 3 is 1/2 minus its sine, square root of 3 divided by 2i. And if we check it, we just put a 1 minus pi over 3, and we get the result that we wanted. So now you can move to do the final 2 exercises, and in the end you can also do these 4 extra exercises.